Good afternoon, everyone, and welcome to this week's CAN seminar. Today, we are very delighted to have Professor Phil Krein as our speaker. Professor Krein is the Grainger Endowed Chair Professor Emeritus in Electric Machinery and Electromechanics at the University of Illinois Urbana-Champaign. His research focuses on electric vehicle drivetrains, battery management, and grid interaction. He holds a doctorate in electrical engineering from UIUC and is a fellow of IEEE and the U.S. National Academy of Inventors. Professor Krein is also a member of the U.S. National Academy of Engineering and a distinguished lecturer for the IEEE Transportation Electrification Council. Everyone, please join me in welcoming Professor Krein.
All right, thanks. I know you've had a theme of electric vehicle charging and infrastructure throughout the term, and I want to give you maybe some contextual perspective here, and we'll hope that maybe it gives you some slightly different things to think about than some of the others you've heard about. And I want to credit my student Raya Mahoney, who's done a lot of the hardware work that we're building up with this right now. But I want to talk about ubiquitous charging, okay? How do we make it possible for everybody to have electric vehicles? How do we make it so you don't have to hunt for infrastructure? Why is everybody trying to make this problem so hard? And hoping that that will work for me. I need to wake it up, I think. Yeah. Should work now. Okay, good. Let me acknowledge support from our center in the ECE department, from our joint institute in China that actually has supported some of this work, and for the Institute for Sustainability, Energy, and Environment here on the campus. We were just actually meeting with them at lunchtime, and some of this work actually came out of the NSF Poets Engineering Research Center. So lots of contributions, right? So it's hard to pick out any particular one that's dominant. So quick overview, I would assert that 95% of passenger vehicle charging can be addressed with existing technology, maybe not existing outlets, but existing technology very cheaply, very quickly, maybe even immediately. And there are analogous opportunities even for trucking applications. We'll look at some of those. How do we use what we have? How do we add basic access on top of that in an easy way? The goal that we're trying to get to is how do I make the cost of recharging basically equal to the cost of electricity? I pay roughly 12 cents a kilowatt hour for electricity in my house. I don't want to pay any more than that to recharge my electric vehicle. In fact, I'd like to pay a lot less than that, and I should be able to do it. Okay. You all know this. Why do we have electric and hybrid vehicles? We have them both to reduce energy, but also to make it more flexible. In central Illinois, an electric vehicle basically runs on nuclear power because of the Clinton plant. That's good. In many places in California, I run on solar power. Granted, in some other places, I run on natural gas or even coal. Is still better than running on gasoline, but not as good as it could be. Emissions reduction, certainly carbon, better opportunities for operation control. It isn't true that autonomous vehicles are always electric, but it is true that it's easier to adapt an electric vehicle for autonomy than a fuel-driven vehicle. And of course, the grid interaction is part of that as well. Now, big transition. You know, during your careers, we have a massive energy transition that will happen. Granted, there are plenty of politicians who seem to pretend that it won't. The economics will simply make that an absolute. It simply will happen just because the existing opportunities will be too expensive and people will do it in a different way. But everybody overestimates the cost of these transitions, and frankly, I think they underestimate the benefit. I love these two pictures. They are legitimate, typical pictures. You know, I was in New York in 1973. Yes, that's what it looked like quite routinely. That isn't the worst day. It's a typical day, okay? And here's a typical day in 2021. right? It didn't have to be like it was on the left. In China, people are starting to figure out that Beijing doesn't have to look like that all the time. Okay, they're still trying to figure out the whys and wherefores of how you deal with that, but it's no longer, we no longer accept that as the price of progress. This is a very important fallacy. There are lots of people who insist that an electric vehicle has to be able to do anything you can do with a fuel-driven vehicle. That's great, but it doesn't make sense in reality, right? When I drive around Champaign, Urbana, there are lots of different kinds of vehicles. There are people driving Ford F-150s, some of them to the grocery store. Some of them are farmers who legitimately need a big piece of equipment. There are people driving little SUVs and people driving all kinds of vehicles, right? Differentiation is absolutely the norm in transportation, right? And we can tell, talking to people, that electric vehicle owners don't use their cars quite the same way they use fuel-driven cars. They do things a little bit differently. Some are things you wouldn't expect. I mean, for example, my electric vehicle, if I want to drive 4 blocks to the park, okay, actually, with my gasoline vehicle, I would have walked. With my electric vehicle, I just get in, push the button, and drive, because it's trivial. That's probably not a good thing, but it's something that's much easier because of that. Now, the reverse is also true. If I need to drive someplace that's far enough away that I'm going to have to use fuel, I start to think about, do I really want to do this, or can I find some other way? This is a great picture. I found this picture, and then Martin Eberhard, the real founder of Tesla Motors, told me what it was, okay? This is a picture of a horse stable taken in roughly 1910, and somebody has wired it up to be an electric car stable. And you were a wealthy person who owned an EV, and the idea was you would take your chauffeur and have him take your car overnight to be watered and fed at the stable, and it would come back charged and ready to go the next morning, and then you drive around, okay? They're treating the vehicle as if it were a horse. Okay, so the car is emulating a horse. So why in the world in the future would I use a nice, clean, easy electric vehicle to emulate a gasoline car? That's crazy. Okay, so it's a fallacy. We just don't have to match things up, and we don't. Charge infrastructure, of course, is considered to be a big vehicle. Should we really emulate that, right? This is one of my favorite pictures, very typical. You've seen these, right? Fast charger. Look how desperately a team of engineers has worked to make it look as much as possible like a gas pump. Okay? If they did that at home with my appliances, I would be crazy upset, right? Everything would be too big. It would be crazy. I don't do things that way. It doesn't make any sense. I'm the electrical guy. It makes no sense to me, right? So the question is, can I just use regular outlets? Can I make it easy? Can I just use retail electricity? How do I make this, why do I have to make it so hard? And part of the other thing is that some people are in this mode of, I need an electric vehicle filling station. Okay, well, the filling station model breaks down, right? And there's a reason for that. A filling station is storing this volatile, explosive, really dangerous fuel, and they have these huge underground tanks, and you fill it with this stuff, and that's enough for roughly 1,000 vehicles, and that works. And I certainly don't want it at my house, right? I don't want to store gasoline at home, maybe a little bit of it for a mower or something, but certainly not enough for my car, right? Well, that doesn't map so well for EVs, right? My house has electricity. Why do I have to go someplace else to get electricity? That doesn't make sense, right? So the filling station model breaks down pretty fast. There's a business model problem, okay? And we see it very quickly. EV owners just don't want to go to filling stations. I have a plug-in hybrid. okay? I hate going to the gas station. And fortunately, I don't have to do it about once or twice a year, okay? Every other time I'm filling it with electricity and I do it at home, it's trivial. Okay, well, the very first slide talked about the 90 and 95% challenge. Let me walk through this, okay? This is a map of daily vehicle miles traveled in the United States. Average daily car travel is 46 kilometers, but the statistics, and we'll show you more detail, less than 5% of trips actually exceed 50 kilometers. And 95% of the trips are linked to about 90% of the energy. We've actually gotten data from China. They're almost the same. They're not nearly as comprehensive as the US data. They're not anecdotal, but they're much smaller data sets, so forth, but they're very similar. So the 90% challenge is I'm really trying to figure out how to support daily driving needs. And I have to be a little bit careful because it turns out, some people find this counterintuitive, the distances are lower in the densest urban areas. You know, everybody thinks that people in LA drive forever. Well, people in West Texas drive forever. Okay, those are the places where it's 100 miles to go to the grocery store. You know, and those people are not interested in conversations about short range electric vehicle driving. In urban areas, it's a different story. Things can work out. And by the way, this chart reminds us that there is a very significant urban-rural component to the whole infrastructure development that we better pay attention to. We can't just trivialize and do up the cities. And that's actually another talk, but I'm happy to answer questions about that issue as we go on too. Well, it's misleading. Most cars actually run multiple trips a day. This is daily total use, so that helps. But I have to analyze things in more detail. So we actually took the US Department of Transportation household travel survey data. The most recent version is 2022. You can argue it's a little bit skewed because of COVID time, but that's all right. There's a very specific procedure for trying to get, it basically is samples of trips. And there's a procedure to turn it into day-by-day driving, which we went through in quite a bit of detail. So here is the histogram of daily miles for passenger vehicles from that database. And for example, these are cumulative numbers. So 50% of them are less than 15 miles. So 15% of the time, 50% of the time, people drive a vehicle less than 15 miles in a day. Okay. And 90% hits right here, 64.5 miles. Okay. And the 95th percentile is out here, roughly 97 miles nationally. The sample, if I remember correctly, is about 7,800 trips from different households. So it's a pretty good sized sample. It's been chosen very carefully. All right. I want to convert that into energy, and Raya decided to pick off this particular vehicle, Kia EV6, because it's a small SUV. It's not a trivial car. It's not the most efficient. It's not the least efficient. It's kind of typical. In the official federal combined highway cycle, it consumes about 280 watt hours for each mile traveled, 175 watt hours per kilometer. Okay, so I can use that as kind of a comparative baseline. Now, I want to use that. Okay, 120 volt outlet. Anybody who understands that, the circuit breaker behind that is going to be rated at 15 amps or 20 amps. The National Electric Code says you're not supposed to load it more than 80% for anything that's connected for at least 3 hours. Okay, fine. So I'll call that a 12 amp source. That's a little bit under counting, but that's okay. That's totally legitimate. Here's an outlet in China, very similar to one that I might find in Europe, except for the format. 220 volt. The circuit breaker behind it typically 16 amps, maybe 10 amps. So I'm going to derate it down and call it 8 amps. Okay. Multiply those numbers together, you get 1.44 kilowatts over here, you get 1.76 kilowatts there. Okay. It turns out one nice thing about this number is it actually wraps in the charger efficiency. That's the number from the wall. So I don't have to have conversations with people, oh, is the charger efficient or not? Well, this is what the car needs from the wall plug and accounts for all the losses along the way. That's good. That's helpful. So now I can do a comparison. So let's see, 1.44 kilowatt hours, 280 watt hours a mile. That's 5.1 miles per hour charge rate. Tesla likes to use miles per hour for a charge rate for comparison. And the other one is 6.25, 10 kilometers an hour. People say, wow, that's really slow. Yeah, it's really slow. But you know, a passenger car in the United States on an average day is parked about 20 hours. Okay? 20 times 5 is bigger than the numbers we had on the other histogram chart, right? Okay, well, I can start walking through this, and I realize that if I take the miles traveled and the Kia and wrap them around each other and say, okay, how much energy do I need? Right? The average is 9.1 kilowatt hours per day. Okay. Is that a big number, small number? I should probably realize that the last 5% is long distance, and in those cases, people are going to do something different. Okay. If I'm trying to drive from Champaign to St. Louis, certainly to Kansas City, okay, I got to plan out and figure out where I can charge reasonably quickly along the way. And by the way, in that situation, I'm happy to pay premium price because I don't do that every day. I don't do it every month. You know, every now and then I'll do that. So if I pull those off and say, well, those people are going to have to be provisioned separately, I end up with 6.3 kilowatt hours per day as the average of what's left. Again, is that a big number, small number? We'll walk through that, right? And here are the percentiles. These are the percentiles from the original data. So you get an idea of what happens. Well, okay. In 8 hours, I can cover 80% of the needs, okay? If I charge my car overnight at home, it's going to be closer to 12 hours, and I'm pushing 90%. If I can plug my car in at home and at work, I'm over here somewhere, okay? And if I can plug it in every place I park, I'm way out here, okay? And that's with that wall outlet, okay? There's nothing special about that. Now, if I'm a little more careful and I say, well, you know, that's kind of slow. I'd like to do something a little more flexible than that. Okay, fine. I'll put in a 240 volt outlet and draw 16 amps out of it. That's actually what I have set up in my garage. It's quite trivial to set that up. Now 8 hours gets me out here. I'm basically the 95th percentile. Life is easy, okay? From an infrastructure standpoint, this is real trivial. This is only a little less trivial. You know, it's not hard, and I cover what I need. So for starters, I say, wow, you know, obviously there's a significant opportunity here. I need to think about this more. Well, how much infrastructure do we have? How much do we need? The usual view in the US, there's a number that gets updated every now and then on whitehouse.gov. They say we got about 130,000 charge points. Well, by code in the United States, every single family dwelling, every two-family dwelling is required to have an outdoor outlet. And it isn't always true that it's convenient to a parking place. but more often than not, it actually is. Okay, there's more than 100 million households in the United States. So there are actually millions and millions of outlets out there now. Okay, not used for this purpose, but there they are, and not necessarily convenient. We can do more than that. I took that picture on a street in Lincoln, Nebraska. Okay, I think that outlet is supposed to have a locking cover on it. I don't care, right? If I have an EV, I can plug it in. Probably it'll take a while before anybody notices enough to fuss at me. That one I doctored, okay? But you get the idea, right? This is actually a picture of a box over in lot E4, right, on campus, across from the State Farm Center, right? 1, 2, 3, 4, 5, 6, 7, 8 receptacles on it. Okay, EV charging points. This picture is on the outside of the ECE building. Okay, so there's stuff all over the place, right? And some people have figured this out. Okay, this is my favorite. In Finland, there are about 3 million cars. And it turns out that, you know, because they have nasty winters, they like to have electric block heaters on their engines to keep the oil from freezing up, and they like to plug them in. Okay. It also turns out that the power drawn by those things is about 1.5 kilowatts, the same as the charging level I'm talking about. And somebody realized that they already have 1 million block heater receptacles in parking lots in Finland now. And all they had to do was rejigger the software so they wouldn't have the same time limiters on them and put up a little sign that says EV charging, right? Bam, right? 1/3 of all vehicles in Finland instantly provisioned for charging. And of course, they're not electric yet, most of them, right? They're way ahead of this, okay? Here's a beautiful picture that I got from from one of the news outlets in Saskatchewan, right? In Canada, of course, they're used to block heaters as well. Some of my mechanical engineering friends look at this and say, oh gosh, the hazard, oh, it's not safe, it's terrible. That happens all the time, all winter. You know, somebody's plugged in their block heater and plugged into the receptacle. You know, there's a ground fault interrupter on it if it gets wet. Yeah, it's electricity. We understand it. It's not a big deal, right? I look at that and I see a whole forest of EV chargers, right? No cost, no issue. And I asked the people there, well, how do you get people to pay for this? They say, well, what are you talking about? They already have to pay a little bit of money to park, so, you know, it's fine. Okay. Does this really work, right? 5.1 miles an hour, 12 amps. Yeah, well. Now, okay, people like to ask the next question. What happens if I put this in a big parking garage and everybody shows up with an EV and they all want to charge at once? Okay, let's take a parking structure and let's set it up for 100 EVs. And let's assume we don't bother with any control, no incentives, no discounts, just plug it in, whatever. Okay, we already did the number. The average need is about 6.3 kilowatt hours from that histogram, right? So 100 cars, 6.3 kilowatt hours, that's 630 kilowatt hours, all right? If I could somehow really spread that out, I just said I wouldn't have control, but if I spread it out, on the average, that's 79 kilowatts. Is that big or small? Well, the elevators and the HVAC in that parking lot probably peak at a number higher than that. Okay, very likely. And if I coordinate just a little bit, I can kind of handle it. Now, remember the maximum rate per car was 12 amps, 1.44 kilowatts. even if they're all 100 going at once, it's 144 kilowatts. That's really not that big a number, right? And 6.3 kilowatt hours at this rate, 4+ hours. So sure, I can tell people, you know, you can have a 5% discount if you program your charger to start at noon instead of at, you know, 8:30 a.m. when you get to work, whatever, right? It's again, we don't have to make it hard. And every EV I've seen, every modern one, has a programmable time thing on the charger. So it's just not that hard. By the way, that number is kind of a typical number for the design of a fast charger. Okay? So the infrastructure ratings for one fast DC charger can support simultaneous daily need charging of 100 cars. Okay? Now, you know, the cynic in me as a researcher says, well, then why am I doing any research on fast DC charging? Come back to that question, because there are positive reasons for that, but why would I put them in that parking lot, right? I want 100, not one, okay? And by the way, in the big parking structure on campus on University Avenue, there is exactly one space provision for the people who own permits to that lot, and there's the outlet behind it, okay? So there's one person allowed to charge at 1.44 kilowatts. Yeah, you know, I don't know whether they're trying to get me to use the fast chargers or whatever. Low cost, that cable comes with the car, the power electronics come with the car. The only thing provisioned in the lot is the receptacle, okay? And the energy cost then basically is at the retail rate because it's coming out of a regular receptacle. Well, what about faster, right? People like dedicated level 2 charging. You've seen these things, right? And the rate can be quite a bit higher, 40 kilometers an hour. That sounds lovely. That's still too low to support long distance driving. Okay, I still have to charge for a long time if I want to go several hundred kilometers. And it doesn't help me with the daily charging. If I'm going to be parked all day or overnight, why do I need that, right? And sure enough, campus survey that we looked at the data from says the typical usage of those things on campus is about 8 hours a month. Okay. The underlying question that I think people underestimate, the one I was just parked at a few minutes ago before we came here said maximum 4 hours. Big warning letters, okay? Am I going to have to move my car? Are you kidding me? I have to leave my place of work and go move my car because you didn't provision the EV infrastructure correctly? I have to fix your problem by moving my car? Oh, seriously? And this thing costs a lot of money. There's a fair amount of infrastructure. The charger pricing is going to have to add a premium to the energy costs to cover that. It has to. There's no way around that. So I look at that, I look at this, I look at that, and I say, I'm an engineer. Is this an engineering solution to the infrastructure problem? Okay, I'll let you think about that. All right. Now, this fine lady seems to be very happy with her, with the things she found there. She's not going to be nearly as happy when she gets the bill and realizes she's paying 50 cents a kilowatt hour to charge her car, which is a typical rate, by the way. It's typically what they're charging. Well, okay. What about some of the use cases? And we did this for small towns in Illinois. One of them is employees and residents. They're parked many hours a day. They should be able to use the basic infrastructure. Visitors coming in and wanting to be there for a few hours to do stuff, visit a museum, shop, and so forth. Maybe they've got 3-4 hours, might work for them. Somebody who wants to come in and have dinner and charge up in an hour, okay, level 2 has some merit for them. right? And maybe they're willing to pay a bit of a premium. So it's nice, right? But, you know, again, there's my picture from Lincoln, and here's a doctored one from a couple of parking meters. A lot easier to put basic receptacles in a lot of places, right? And if I have that, you know, there's still the question, who pays? Charging not free, right? Energy's not free and the infrastructure is not free. Who pays? Well, I would claim that that kind of infrastructure gives lots of business models, right? I can have an app where the driver pays, either added to the parking cost, or maybe if we have it out in a neighborhood, maybe there's a parking permit that you bought that gives you basically unlimited access to charging. We can do the math on that. Maybe you have a phone app to turn the thing on and off and to tell it what to charge to. In the long run, I hope we can figure out roaming billing so that, you know, if I'm at my grandmother's house, I can tell the utility to bill me instead of billing her. You know, there's many, and you could probably think of 20 more, right? The other direction would be the premises or the location pays. In other words, energy as a service, right? Come into my restaurant, you can charge up. Maybe there's a point of sale activation. I go in the restaurant and say, hey, I'm going to have lunch. I want to charge my car. Well, what space number are you in? Well, I'm in space number 14. Okay, push the button, it turns on. You know, charging as an incentive when we're shopping, solar canopies, we are seeing that kind of thing in the West, where people will put in solar charging and they have an EV charging thing related to it. Charging is not free, no question, but you know, we were having a conversation informally with a couple of people last week, and I realized that the analogy to Wi-Fi is there. Okay, some of you probably don't remember this, but when Wi-Fi really started coming out 10 or 15 years ago, there were all kinds of places where you could subscribe, and you know, everybody wanted a monthly fee and so on, right? So you know, who pays? The question was, what's your credit card number, right? It still happens on an airplane, right? They still want to know that, but everywhere else, right? You know, we all know it's not free, but we all expect it to be there, right? Most businesses, hotels, restaurants, everything else understand that Wi-Fi is now part of the service cost. It's a cost of doing business. It's basic infrastructure. I can assert that it's not going to be very long before any half-intelligent hotel chain realizes that they need to have a bunch of outlets in their parking lot, and it's fine. At 1.44 kilowatts per each, you know, yeah, you just do it. Now, all this is to not ignore that you still have to have fast charging. You're still going to need that for long distance. There's no way around it, okay? But it's the 10% problem, not the 90% problem. And yes, in that situation, I'm willing to pay a premium because I'm doing something unusual, right? Frankly, I think the truck stop people, Loves and you know, some of the others, QT, I think they'll figure it out. You know, they have business models. They understand how this kind of thing works. And by the way, they're starting to install the things. We know Tesla has their superchargers in many places. As some of you know, they're starting now to charge people for it, and you start to get an idea of how much it really costs. This is a setup in China. You will notice that there are exactly 0 vehicles plugged in that photograph. And by the way, I've been by that place many times in the last 5 years. I don't think I've ever seen a vehicle plugged in. Okay, too expensive. Trucking, non-trivial, right? So here's the other part of the last 10% problem. But, you know, we have data. Here are truck volumes on US highways from survey data from 2017, okay? And frankly, that map tells me where to put fast charging infrastructure, okay? Not entirely, but it's a pretty darn good way to get started, right? And of course, the biggest blob on the map is Chicago. So I'm reminded that, Illinois and the area around Chicago, Indianapolis, and Indiana are the places where we should, emphasize some of the fast charging infrastructure. But again, I know where to put it. It's not everywhere. It's convenient to where people are driving long distances. The other thing that enters into this for trucks, of course, is rest breaks, right? So when you have a single driver in a truck, a driver is actually required to take a 10-hour consecutive break every day, and a 30-minute break after every 8 hours of driving. So again, the question, and by the way, we don't have enough parking spaces for all the trucks that are moving around right now anyway. But if we could provision all of them to allow people to plug in, things would be different. There's a picture I managed to find on the web, and the Tesla people aren't given much data, but of course the writers are actually driving the things around trying to get their own data. The estimated capacity of that thing is about 850 kilowatt hours. And the usage about 1,700 watt hours per mile when it's fully loaded, which is really helpful data. So if I want to recharge fully in 10 hours, I need 85 kilowatts. That's, of course, a pretty high number relative to a passenger car, but a 10-hour rate is pretty modest for batteries, so it's not that big a deal. And I begin to understand how to provision that. Now, Tesla claims that they can recover 70% of the energy in 30 minutes. You do the math and you get pretty big numbers. And, that sits in here. But again, I don't need that during the 10-hour rest break. I'd rather have a lot of them, right? Effectively, again, one at every space rather than trying to be in a line waiting for a fast charger so I can get going. School buses are actually easier, right? They're only used a few hours every day. And they sit at a depot or a fixed spot almost all the rest of the time. And it's not that hard to do the math and figure out that, yeah, I'd like to have something in every space. My favorite is an anecdote that we were hearing about local delivery folks, and I won't tell you which company, but basically they were telling us that every night, when their drivers come back, they have to wait in line to put fuel into their vehicles, and it takes a long time. And we realized that, oh, that's lovely, so go to electric and a fast charger. What's going to happen? They're going to wait in line every night to use the fast charger, okay? On the other hand, if they had sort of a minimal size charger at every space in the lot, right? Then they pull in, plug in, and go home. The amount of money saved is huge in many different ways. So of course, in the long run, that's what they're going to do, right? It'll save them lots of money. Receptacle every space, plug in, forget about it. Similar for the school bus, right? Now, we're actually working on this concept, okay? We actually have these boards. Several of these boards are in long-term testing right now in the lab. The notion is to give a little bit of intelligence to an outlet for very little money, $20, $25 kind of level, partly so that Wi-Fi can turn it on and off, partly so that we can get some data, because, it'd be nice to have some real data on what's going on here. And I won't bore you with too many of the details, but a lot of design aspects to make sure it can work on 120 volts or 240 volts, and then it can manage its own safety, turn things off, and add protection. So that's pretty important. But here's what I'm wrapping up now a little bit. I want to leave you with a little bit of this. So one of the really important things is that if I plug my car in and I expect to be charged up in an hour or so, that's lovely, but I'm hitting the grid with a lot of power and I'm not providing any flexibility. If a car is plugged in, it is flexible load, okay? And here's a scenario we did by comparison. It's hypothetical, but it's based on real data. We said, okay, let me do the example where I plug my car in, I tell it you can start charging at 9 p.m. and I want you ready to go 100% at 7 a.m. tomorrow. And you, car, I want you to go on the internet and get the hour by hour utility price and figure out the charge sequence overnight that will minimize the energy cost to me. Okay, that's not a hard problem. Any of you could figure that out, right? And here it is, stepping through the different levels. And of course, at 1 a.m. is when you see the highest draw because that's when the power's the cheapest, right? I come back the next day, my car's full. I'm very happy. I have minimized my cost. My utility says, wait a minute, I can do better than that. This noisy signal is what's called the area control error. It's the frequency error in the grid because the load is moving around all the time. And they're saying, well, yeah, we'll start at 9 p.m. We'll guarantee you're at 100% at 7 a.m. And in between, we're going to control you to track the control error, okay, to therefore maximize the dynamic benefit to the grid. Okay, so the clever grid operator is going to say, you know what? You thought this was minimum cost. You let me do that. I'm going to take off another 30%. Wow, okay, go ahead, right? And I can do this, right? I can move my charge around. It's just a modulation challenge. It never goes above 6 kilowatts. By the way, it never goes below 0, okay? And I'm happy because my car's full. My utility operator's happy because the grid dynamics are being offset. Everybody's happy. And it only works because that car is connected continuously all that time. Okay? A connected car is a flexible car. Flexible load is something I can monetize, and that's good for everybody. Okay? Very important to notice it never goes below 0. Because a lot of people say, wait a minute, I don't like this. That means the utility will sometimes pull power back out of my batteries. Nah, don't need to do it. Okay? Just setting the charge level. Not a problem. And by the way, if some disaster occurs in the middle of the night, okay, fine. Maybe I have to turn off. That's one piece of it, right? So, trying to wrap up here. 90% of energy needs, certainly for daily passenger vehicles, can be supported from basic receptacle infrastructure. And I hope that I can get people to help us push the issue of getting ubiquitous access so that you can get energy wherever you park. Trucking is a little bit different, but slow and fast still matters, still makes sense. And we need to expand to make sure that people can find receptacles wherever their vehicles are. Be great to have just a force 120 volt receptacles where people live, where they work, where they park. It's not expensive to put in. It doesn't really impact the grid very much. We can get to about the 10 kilowatt level needed for delivery vans and school buses. That's probably adequate. That's more than at home, but it's not that hard to get to scale. Long haul trucks at that 85 kilowatt level, that's fast charging for everybody except long haul trucks. Certainly needed, and need to figure out how to get that cheap. That's tough. That 30-minute charging that Tesla likes to talk about, 1200 kilowatts, that's a lot tougher issue, and that's why people spend lots of time trying to understand how to deal with this. When you start talking about charging embedded in a roadway, that number means more than this number, and that's a good thing. Okay, I should be able to match up with the slow rates to get this to work. Okay, and I want to thank some of the other people who participated in this, and I hope we have time for discussion. So thanks. There's one in line and we'll get here in a moment. Let's take one in the room, then we'll take one in line, okay?
Thank you so much for the presentation, Professor. It's been really engaging today. But I will have a question for you, because I think the technical solution is there, but I think it is more like a social problem. Because how will you explain that despite the fact that the information shows that 90% of the time you don't really need to have that much autonomy, this is a big problem for light vehicle owners, that they feel so much mind rage anxiety, despite the fact that they don't need it.
Yeah.
And I think it also happens to normal devices, right? Because right now, battery autonomy is pretty much one of the main features for people to decide which device to buy.
Yeah. Okay, so trying to repeat part of that question, part of the issue, of course, is just social acceptance. You know, I talk to Tesla owners, for example, who say, no way am I going to use that. That is my infrastructure. It's just too slow. I can't make that work. It's nonsense. And other people say, oh, you know, I'm really worried about range anxiety. Where am I going to plug in? Okay, the point is to be able to plug in every place your car is going to be, right? The anxiety goes away if every place I pull in, oh, look, there's an outlet. Oh, it says EV ready. Okay, there's no reason why we can't get to that point. And that will change things. And actually, the people I know who have electric vehicles say, yeah, you know, you're right. If I just plug in every night, it's fine. You know, it takes a while to get used to that. But yes, we're not there yet, right? I mean, I can't find an outlet everywhere I park. It doesn't work that way now, right? I got to fix that. But I guess the other piece of that point is it's much easier for me to imagine a bunch of receptacles with sort of a parking meter format in a low-income neighborhood where people don't have a garage and they don't have a good place to park, right? Having things that look like parking meters that have outlets where you say, okay, you need a local permit, that sounds real low barrier to me, right? As opposed to saying, oh, well, you're in this neighborhood and we're not going to provision it. You got to go do the fast charger. They'll be happy to give you power. They're going to charge you $1 a kilowatt hour. No, that's just not right. So yes, we have to get into a provision that people are used to, right? People are used to parking meters. I don't think it's that big a deal. But yeah, right now we're not there, and we need to be to the point where everywhere you park, oh yeah, look, I can plug in there. I can plug in there. Oh, look, it's all ready for me to go, which, by the way, is happening now in Finland and Norway, in some other places in Europe. My Norwegian friends tell me, you know, there's no problem. Everywhere I go, I find a place to plug in. It's fine.
Take the question on Zoom.
Yeah. I see, Professor Barkin has a hand raised on Zoom. Hi, Chris.
Hey, Phil. Great talk. Really interesting. I want to ask you a question, though, which is, what if your assumptions about the daily miles traveled and the ubiquity of outlets is completely reversed?
In what sense do you mean? In what sense do you mean reversed?
What if the majority of daily miles traveled are very large, very long distances, and, as I say, electric power outlets are not ubiquitous?
Well, okay.
Well, and you should know, just from looking at what's behind me, you should know where I'm coming from.
Yeah, sure. Well, first of all, it's going to depend on use cases and modes of transportation, right? I mean, there's still the issue of if I'm a rancher in West Texas and I literally have to go 100 miles to go to the grocery store, okay, and I'm going to be in that grocery store for an hour, I would really like my truck to be pretty much full when I'm done. Okay, and just plugging into a regular receptacle is tough for me. And I'm not blowing that problem off, but I'm kind of hoping that the local Loves and the QTs and the pilots say, hey, I understand how to deal with that. You know, I got my dining room. I want to have the charger provisioning there. I want to make sure that that person, after they go to the grocery store, comes and eats lunch at my place and plugs in and goes home with that. Now, the other point, Chris, you're right. I've been emphasizing passenger vehicles and the infrastructure appropriate for them. And of course, basic receptacles is a great way to go. You're sitting in front of a nice pantograph there in a train system. Although still, right? The point of those systems is I actually have pretty good grid access and I should take advantage of it, right? So, you know, the other part of this is I'm still waiting for, when do we put the electric infrastructure along Interstate 80 all the way from San Francisco to Chicago and, you know, try and make that part of the long distance problem a lot easier, right? There's a relatively limited number of miles of interstate highway that we need to go after to really get that going.
Yeah,
But we got to have ubiquitous access to you know, handle the passenger EV aspect.
yeah. So let me just clarify what I'm getting at, which is North American freight railroads, the majority of their daily miles by a long shot are very long distance, 1,000 miles a day or more.
Yep.
And electric power of the scale that they need to charge, if you were to use battery electric locomotives, the amount of power that they would need to recharge those batteries is not ubiquitous, and that's the point. So I totally respect and get and appreciate that what you're talking about is passenger vehicles, and that's a great set of observations you've made today. But we've got a different problem to solve in the freight rail industry. The image behind me could be the solution, which is to electrify, but the jury's still out on that one.
Well, but let me put that question to you. What would it take to electrify the Union Pacific line from San Francisco all the way to Chicago? And why wouldn't we do that? There's plenty of room for it.
A very large amount of capital. That's what's the big challenge.
Sure, but maybe not per mile, right?
No, it's pretty big per mile, trust me. That's why it hasn't happened before already. But I will say we just had a whole session on this related to this topic at the conference I sponsored this week on campus. And there's a new concept that's very interesting in terms of reducing the capital cost, and that's called discontinuous catenary, or nicknamed disco cat. And the idea there is you put some batteries in the locomotive so that the most expensive areas don't have to have catenary.
Right. Very, very much analogous to electrified roadbed.
Yeah.
You don't attempt to do the whole thing. You pick and choose and do the easiest sections. Absolutely. Okay. Yeah. Thanks.
Thank you.
Professor Krein will be here for a little bit if someone wants to talk to him. But thank you, Professor, for the invitation.